All right, a very, very warm welcome to this webinar about environmental statistics. We are very delighted to have you all with us today to dive deeper into this topic. My name is Mattias Strandberg. I am the Secretary and Event Coordinator for the Swedish Statistical Society, Statistikfrämjandet. And today we have with us two doctors and one expert in environmental statistics who will guide us through all of this. I will be with you throughout these 2 hours as well to sort of help you along and also make sure that everything runs smoothly. So if there are any problems, just send me a chat message in the chat window or send me an email at sekreterare@statistikfrämjandet.se and I will ensure that everything runs as smoothly as possible. So with us today, we have Michelle Nygren, who defended her PhD in 2022 at Gothenburg University. Since then, she's worked with hydrological and hydrogeological modeling, currently at the Swedish Geological Survey. We're gonna first off hear from her and her thesis impact on climate variability on dynamic groundwater storage in mid to high latitude countries. She's very interested in statistics as a tool to understand the hydrological cycle and the historic relationship between meteorology and hydrogeology, which is a topic that she's very passionate about. Our second doctor is Dr. Dmytro Perepolkin, who is a researcher with a robust interdisciplinary background and an MBA in finance and strategy from California State University, East Bay. We're going to be hearing from him after Michelle and his thesis, Scientific Methods for Integrating Expert Knowledge in Bayesian Models. And in his thesis, he focused on developing probabilistic models that integrate expert judgment with data for environmental management. And the work bridges the gap between data analysis and decision analysis with a particular interest in how complex multi-objective decisions are made in the environmental domain. After both of those presentations, we will take a very short break so you can all stretch your legs, and then we'll come back and listen to Viveka Palm, who's worked with environmental and economic statistics since 1996 in various positions, mainly at Statistics Sweden, SCB. As part of her work, she has also served as an adjunct professor at KTH and recently worked at Eurostat as a director for the Department of Sectoral and Regional Statistics for the past 3 years. And she's now back at Statistics Sweden. So Viveka is going to comment shortly on the two theses that we will be hearing about. And then we'll finish it off with a panel discussion talking more about how we can make science and practical use come closer together and how we can actually utilize all of this research that's being done in our universities throughout Sweden. So with that, I would like to welcome Michelle to turn on her webcam and start her presentation. Welcome.
Yes, thank you. Let's see. Do you see my presentation?
We see your, there we go. Now we see your presentation. Excellent.
Okay. This is absolutely the wrong slide to start on. I'm sorry. This is the first slide to start on. Yes, so I'm not currently there anymore, but I did my thesis at the Göteborgs Universitet, University of Gothenburg. And as mentioned, I just want to emphasize that my work is focused on the environmental topics of climate and groundwater storage. And I've applied some statistical methods to analyze the data, but please bear in mind that this is not a dissertation about statistics. However, I hope to show you how I have used statistics. Now it's been important for me to identify patterns in the hydrological cycle, but I might not go so much into detail. So the title of my thesis was Impact of Climate Variability on Dynamic Groundwater Storage in Mid and High Latitude Countries. And I'll just start now. So why are we interested in this? My thesis started in 2017, so a bit around the time of the 2018 drought that maybe some of you remember, or many of you remember, I don't know. In these pictures, you can see, let me check. Do you see my mouse? Is this maybe the laser pointer? Do you see my mouse? Okay, I guess you see my mouse.
Yes, we do see it now.
Okay, perfect. This image here, this is of Skåne in southern Sweden and this bit of Denmark here. And this image was a satellite image taken in August of 2017. And this is the same area taken in August 2018. So you can clearly see how these fields are all very dry in the same area. And well, here's a close-up, another close-up. And here we have the result of some forest fires. So these are drought events, extremes, but they're related to water fluxes. So it didn't start like this, obviously. It was a very hot summer, but it was also a year of very little precipitation. So droughts in the agriculture and forest fires, they're all related to water fluxes. So meteorological droughts propagate through the hydrological cycle. The concept of drought propagation looks like this. So we have an anomaly, say in precipitation, and this sort of propagates through the system. This looks very linear and easy, but actually all of these different stores, soil moisture is a water store, stream flow is a water store, they all interact with each other. So for example, once you get to groundwater drought, it can in turn affect soil moisture and strategies to mitigate drought, such as artificial irrigation, for example. Let's see. These are just some headlines to show you that this drought affected large parts of Sweden, where it was mainly impacting agriculture and forestry, but also there were some water scarcity issues. So then we get the question, are these extreme events or is it the future normal? Like, how will it look like? How has it looked like in the past? So to understand this, we sort of need to understand the water cycle a bit. And this is a very simple conceptual image from the school book, of course, but just to show you that we start with precipitation, and then once you have precipitation, things can happen on the ground. So you can have infiltration, you can also have surface runoff, and you can also have direct evaporation, for example, from surface water or puddles. And also from water collected on leaves, you can have direct evaporation back into the atmosphere. You can also have transpiration, where water in the soil is taken up by plants and then transpired back. The infiltrated water can also propagate through the soil to reach the groundwater. And once it reaches the groundwater, it can flow to the stream, it can go back to the soil, it can just move generally underground. The groundwater is the second largest freshwater store globally, and it's a source of more than 50% of the drinking water in Sweden, Finland, Denmark, and Iceland. Norway has glaciers and it's more dependent on those, but for the other countries, it's very important. So underground, we have something called the unsaturated zone. So the water, the ground isn't saturated with water, but then we have the saturated zone where there is a lot of water, and this is what we call the groundwater. So the surface level, we can say, of the groundwater, we call the water table very often, but I will probably use the word groundwater level in this presentation. And then when you have variability in groundwater storage, this water table, the groundwater level will fluctuate up and down. So some fluxes to and from the groundwater specifically, precipitation, as mentioned, is very important, and the sort of balance between precipitation and evapotranspiration you can say can determine the recharge, but there are many more factors at play. Just want you to remember that. But this is the very simple, basic concept. And yeah, once in the ground, the water can propagate, and once it reaches the groundwater level, we have renewal of groundwater, and we call this groundwater recharge. As a side note, capillary forces can create something called a capillary fringe in the unsaturated zone, and this can lead to a direct connection between shallow groundwater and the root system in the unsaturated zone. And this can lead to direct groundwater depletion via transpiration, but just something to interesting to know. Anyway, the data on this that I have looked at looks a bit like this. So here in the top part, we have precipitation going from 0 to 200. And here you have variability in storage represented by groundwater level. And when something changes like this over time, in hydrology, we call it dynamic. So this is a dynamic groundwater storage. As you can see, it doesn't really correspond exactly to the precipitation, which shows you how complex the relationship can be. Yeah. So the variability in fluxes to groundwater are influenced by many factors, and mainly it's dependent on geology, geomorphology. These are spatially changing, and then we have some things that are more spatio-temporally changing, so like such as land use, biomes, and climate. And the climate has been a bit the focus of my research. So here you see a moving image of past and projected Cup and Geiger climate zone classifications. You can focus a bit zooming on Sweden here, where in southern Sweden you have this green, it's called the temperate climate, and then in the north we have this purple zone called cold climate, which is more driven by snow in the winter and snow melt in the spring, and in the south here more rain in the winter and a lot of like a long growing season in the summer. And as you can see, in the later part of the century, we're expecting that this temperate zone will migrate northwards and replace the cold climate zone. So the the objective of my thesis, the aim, was to increase the understanding of climate variability and groundwater system characteristics and how they influence dynamic groundwater storage. So to evaluate possible change to groundwater recharge seasonality, assess impacts of climate variability on dynamic groundwater storage, and explain groundwater drought responsiveness and its variability. So to understand future impact assessments, we look a bit at recent change. I look at the past to see kind of what the future could potentially look like. My data comes primarily from state agencies. The purpose of these maps is just to show you the broadly large regional similarities across the Northern Hemisphere. And now we focus a bit on Sweden, which is this area. This light blue LGM stands for the last glacial maximum, which has heavily influenced the environment in these regions. You can focus on this image here, which just says that in these areas we have local and shallow aquifers, mainly confined to unconsolidated glacial deposits such as Tiv and glacial sand and silt, which is relatively small groundwater storage if you compare globally to Africa, to Americas, to Asia, and so on. And here a bit confusing, I changed the color scheme. So here the temperate zone is in yellow and the cold zone is in green. So my thesis is focused on the concept of the water balance, very simplified, but less recharge leads to declining groundwater levels, more recharge leads to rising groundwater levels. And then I have associated these to a different hydrometeorology, rain and melt. So the precipitation is not always relevant as is rainfall as opposed to snowfall, and snow melt as opposed to just rain. So we're looking at those two. parameters. And then instead, evapotranspiration is very difficult to actually measure. So I've used the potential evapotranspiration, a measure of what could potentially transpire if there was unlimited water. So I use that as a proxy. And then we're also interested in the number of wet days, because it's not always if there's rain or not, it's also how long does it rain for, and like the duration and the intensity and these kinds of things. I've looked at data from the 1980s to the 2010s, as the climatological differences are similar to climate projections, and to be honest, it's also where we have more data. It's like that sometimes. It can look like this. So this is a bit of a messy image, but if we just focus on these lines first, where the solid line represents the, for example, here, this would be the median groundwater level standardized for that month, for that decade, in this case, the 1980s. The dotted line is the same, but for the early 2000s. And here, because the groundwater levels are declining, characterize those as such. And I have characterized them for both the 80s and the early 2000s. So this would be the characteristics, how I characterize it for the 80s and characterize this for the early 2000s. And this is the corresponding hydrometeorology, sort of similar, but on a daily basis. This day, this median is the snowfall. Is generally snowfall this period for this location in the 80s, and in the early 2000s, most of the time, yes. And the same, we have high potential evapotranspiration, just means that there was more potential evapotranspiration than rain. So we have a deficit in water. Green is the snowfall, so there's snowfall, basically, it's too cold for rain. Rain is that it's more rain than high potential evapotranspiration, and snow melt is that the snowfall was, well, the snow was melting. And in terms of statistics, I will show you a bit in the results, but I've applied non-parametric statistical analysis on my data, as it's rarely normally distributed. And I applied Kendall, the TLSN, and the Spearman methods on time series data and other hydrological measures. But I won't go too much into detail about that, unfortunately. To identify anomalies, to look at drought, I've used the method of standardization of groundwater level and precipitation. Is the ranking method, and then for groundwater, you get something called the standardized groundwater level index, the SGI, and the standardized precipitation index for precipitation, called the SPI. Basically, you have the data, you fit it to a normal distribution and get a cumulative probability, and then basically you convert that to get a standardized anomaly to tell you, was it very dry, negative values for dry, was it very wet, positive values for wet, to be able to compare spatially across regions. I did not use the same method for groundwater level data, but I will not go into detail here, unfortunately. This can look like this. So because the groundwater is very common in hydrology to accumulate precipitation when you do this standardization. So you accumulate it for a certain number of months. And here's just to show you how, for this location, which is very slow responding, if you increase the accumulation period from 3 months, 12 months, 24 months, you increasingly get a better fit to correspond to the groundwater level. And then with this SGI and SPI, I have, for the SGI, calculated or done an autocorrelation analysis to get the drought duration and recovery characteristics, and then done a cross correlation from SGI to SPI for different accumulation periods to get the sort of drought propagation and response time. So, messy image. Top row is the 80s, bottom row is 2000 and early 2000s. Left column, winter, right column, spring. So between 1980, there's a shift, clear spatial shift, similar to the climate projections, showing that the sort of the temperate region conditions of rising groundwater levels, more recharge in winter. These conditions have migrated northwards, so the snowfall period with declining groundwater levels is not as common in the south of Finland anymore. And in spring, we have declining levels associated with a high potential evapotranspiration also migrating northwards, so just a sort of temperate hydrological fluxes just propagating northwards. So temperate climate replacing cold climate in terms of the hydrological fluxes. So we have increased rain in winter, decreased snowmelt-derived recharge in the region, and a longer growing season. So starting early in spring. The striped region is an undefined boundary because of the lack of data, basically. This has led to decreased groundwater storage in general. So this was, using the Mann-Kendall test, I've seen that this is statistically significant decline in groundwater level depth for many different measures. And here I show you the median groundwater level depth, where the colors, you can ignore them, but they correspond to different latitudes. And if the dots are in this purple area, that means that the levels were deeper in the latter period. The green area means that it was deeper in the 80s. But generally, they're deeper, significantly deeper in the latter part of the period. And it's important also to look at autumn as it sort of corresponds to the sum of the annual cycle, as the autumn is the start of the hydrological year, as we call it. So to reset the system. If we look at trends, so here this is standardized Sen trends of groundwater levels on the annual scale. Here we have frost-free season trends in the meteorological cycle. Here the water balance, rain plus melt minus potential evapotranspiration, and here wet days. This is the frost season, basically meaning that it was cold during the cold period. And black bounding boxes indicates that it was a significant trend. So generally groundwater levels decline in Finland, and this corresponds quite well to water balance and wet day frequency trends in the summer, so the frost-free season. However, in Sweden, we have very different trends, and our meteorological trends that are, well, not significant, can't really explain this. So probably it's because of other factors that affect evapotranspiration and potentially artificial pumping. Just also want to emphasize that this indicates that ground frost is impeding groundwater recharge. So even though we have more precipitation or more effective precipitation in the winter, is not corresponding, like doesn't show in the groundwater level trends annually. So for groundwater drought responsiveness and its variability, generally in post-glacial settings, groundwater drought responsiveness is 1 year, but there's quite a high range. There's a clear difference between sediment types. So sediment type clearly has a different response time in terms of drought. There's a very large range in sand. And there's some secondary peaks that I think are of interest at about 35 to 55 months here. And I cannot explain them by my analysis, but it could be perhaps due to atmospheric teleconnections or longer memory, maybe something, some influence from surface water. There can be many factors, but it's interesting nevertheless. We have many recurring, many secondary peaks like this, and we have a lot of periodicity in hydrology. So it could be something like that. Oh, I see that I'm a bit out of time. I will just go through this quickly. I've also looked at the connection to other environmental variables, and there is a clear connection to soil thickness, median groundwater level depth in general, land use, drainage density, and annual temperature and annual precipitation. Yeah, since I'm a bit out of time, I think maybe I'll skip through the conclusions, but yes, maybe less recharge because of the migration of the climate in the south, migrating northwards. There's many impacts affecting groundwater trends. And so we need to look at also precipitation intensity and these other things. And the same for ground and drought responsiveness, basically, but post-glacial settings are generally shorter than 1 year, which is different from a lot of the rest of the world, actually. Thank you for listening to my presentation. Yes, I think I will stop sharing.
Excellent. Thank you very much, Michelle. I realized that I forgot to mention that there are now opportunities to ask questions if there are any specifically pertaining to Michelle's presentation. There will also be an opportunity to ask questions of Dmytro after his presentation, and then we will open up to questions to all three speakers during the panel discussion at the end. But I would like to ask you, Michelle, what is sort of the most profound realization you realized when doing all of this research?
Profound realization. Well, I thought I found a pattern, and then I looked more at the data, and I'm like, actually, I don't think this is it. So I feel that the more I look at the data, the more I try to analyze, the more I try to understand, the less I know. And I think that's something that you have to learn as a researcher in general, that the world is infinitely complex. And all we do is try to simplify it to understand it, but it's very complicated and there are many different factors. And just to remember that. Yeah, I think I attributed a lot to frost. I think now I would want to add a lot of more different ways of looking at precipitation, because it's not so simple as the amount of precipitation. As I mentioned briefly, it's a lot to do with intensity, duration of wet periods. It's not only when it's cold at the surface, because it's also difficult to measure ground frost. So I used surface frost as an approximation, but the ground can often be, how do you say, insulated, not least by snow. So there are many, many different factors at play. And to look at such a regional scale is especially hard because it's hard to extrapolate. I don't know. It's just infinitely complex. And I think that was my profound realization. And it's very difficult to talk to decision makers and policymakers and politicians about this, because they just want a black and white response. Statistics can help with that, but yeah, just to remember that things aren't black and white.
Right. Yeah, that is something I think everyone who's done extensive research realizes after a while, that you start getting more and more confused the more you look at the data.
Yes.
Hopefully, that is something that can be remedied with further studies. So if you were to redo it, you mentioned that you would take in a lot of other factors. If you were to redo this research, what would be like the one or two major things you would change?
Yes. One or two major things. I would become a better programmer, first of all. And then I think I would include, I think using rain melt and potential evapotranspiration is fine, but then in terms of wet days, I would include many more different measures on precipitation. You can also use dry days, but it should be similar. But I mean, you can use different thresholds. Just adding more of that. Also, maybe going more into detail on seasonality. And I'm a bit limited by data because I didn't gather any data myself. But just play around with how to do it, and maybe also for the drought, go back a step and you look at the autocorrelation and responsiveness of the raw data rather than the standardized data, because it should be similar. But I think that maybe some information is lost in the standardization process. You need to do some standardization, but maybe not as much as I did. And just look at maybe normalized data, something like that.
All right, excellent, thank you. We do have a question from Claudia from Bremsen. welcome to ask your question.
Yeah, thanks. I was interested in, because you said you had lack of data in Sweden, but what is the type of data that you used for this? Because I know groundwater data is difficult to obtain. So what is the basis of your analysis?
I used groundwater observations from the SGU, the Swedish Geological Survey. But then also I looked at, well, they have, for each observation, they have some characterization of the kind of soil. But often it's not in an aquifer, so it's just a name, basically, with not very detailed information. I tried to look a bit at the stratigraphy, but it's hard. I like core, a core with the sedimentation, and I can see a bit more clearly if there was more clay, for example, things like that. There is some data on soil thickness, but it can also vary a lot in small regions. So maybe high resolution on that. And also I used some data of hydraulic conductivity, but it was way too coarse. I found basically zero correlation because I think it was just too coarse. But to have some more information on fractures in the bedrock systems, as that could mean more or less storage in the underlying bedrock, because that was also very difficult to try to assess on this scale.
Yeah, I was thinking about that different types of groundwater aquifers will have quite different properties, I guess.
Yeah.
And how does that compare to Finland then? Do they measure in a similar way, and do you have the same type of information from there?
They tend to put more wells in defined aquifers, and then they have more information about the hydrology in these aquifers, but then not so much maybe in other regions where there is less storage. But I could find, for example, specific yield for Finland, but not for Sweden. And that's something that was very, also in Canada, they had a lot of information. Well, there they had, like, you can see a 3D model online. Where like you have aquifers, like which one is lying above, which is below, you have the specific yield, you have more stratigraphic information from different boreholes in the same aquifer, and that can give you a more holistic understanding when you're analyzing the data to try to look at details and see what is actually is happening here in this specific case. But different countries come with different difficulties. I found, as I said, high correlation to soil thickness, because I assume there is more storage in the soil, so it could be a proxy for the aquifer thickness in some cases. But in Finland, they have similar data, but very coarse. So it's difficult to compare across the countries.
Thanks.
Excellent, thank you. And with that, I would like to thank you very much, Michelle. We will see you again shortly for the panel discussion. And I would like to invite Dmytro Perepolkin to turn on his webcam.
Thank you.
Welcome, Dmytro.
Thank you. Can you see my screen?
Yeah, we cannot see your screen yet. We can see.
No. It should be coming along. Just a sec. There.
There we go. Now we see your screen.
Perfect.
Excellent. Welcome, Dmytro.
Yep. Thank you. Let's move away. Perfect. All right. Well, thank you for giving me the opportunity to present my work. I've been working on this thesis, Scientific Method for Integrating Expert Knowledge in Bayesian Models. You can see the link to my slides over here with QR code if you want to follow along and take a picture. And there is also on this page, you'll find a link to the thesis, and there will be a link to the thesis at the end of the presentation as well. My thesis was primarily method development, method contribution, and then I also had a case study at the end that applied method that I've developed to a particular environmental problem. So I'm going to come back to that. But bear with me that I'm going to go through some statistical introduction and some details of the model. So first of all, decision-making in environmental management is particularly difficult because we have a complex system with lots of interacting parts. But in any decision, you have these three pillars, three particular things that are contributing, or rather constituting, the decision. We need to consider what we know, that's prediction of future outcomes. We need to have something that we can do, that's alternatives, choices, and we need to have something that we want, which is values or preferences. And they all kind of essentially contribute to decision. There is a picture of that decision maker, committed decision maker. The outcome predictions come usually from the model, and that model is a statistical model that is informed by data. Here it's on the side, you can see that, and it has a specification of a prior and a posterior, and then using that model, you can generate predictions, which would be outcomes for decision making. Expert knowledge is actually essential in all parts of that whole setup, from defining priors to specifying the structure of the model to making judgment on outcomes, on predictions as a predictive elicitation, also specifying what we can do, and absolutely elicitation of values and preferences are essential for setting up a decision model. So expert knowledge is involved everywhere. But today I want to focus on this part, which is model specific, and then kind of look deeper into what's going on there and how expert knowledge can be integrated into a model part of a decision model setup. So statistical models are just special tools for generating fake data. You specify some parameters, and then you turn the crank and you get some fake data that is produced by the model. But in many cases, you want to run it backwards. And in that backward mode, which is also known as Bayesian statistics, you turn the whole kind of setup backwards, and you look at how plausible is the data given particular set of parameters. That's called likelihood. And in this case, you see that it's consuming data and then kind of trying to produce what the parameters could have been for generating that data. So that's the mode that I'm interested in exploring further. A little bit of introduction for a model specification. So defining a model is possible in two different ways, equally adequate, as Toki says in 1965 paper, either through distribution function, it's called CDF, or through a quantile function, which is an inverse of a distribution function. Probability density function, PDF, f of x, is crucial for Bayesian inference, but the quantile function also has its own density, which is called quantile density, and it turns out to be numerically reciprocal to PDF. That's a very, very nice property, which means that this Bayesian inference, the thing that I'm interested in, like the backward, right, running the statistical model backwards, it's possible without a PDF. That's a very great news, because you can use a lot more distributions that do not have explicit PDF, but they have explicit quantile function. And it turns out that these distributions are very usable for expert knowledge. And as an addition, the regression models where the error term is specified as a quantile function called parametric quantile regression has a very useful properties that I'm going to discuss a little bit later. So using these yellow boxes, you'll see these are takeaways from the main papers. In paper 2, I explored this particular type of model specification and what it can be used for. The icon on the left here with the curve going upwards, that's how quantile function looks. And we're going to look at some examples in a second. So kind of wrapping up, giving some examples of the distributions that are specified by CDF versus quantile function. You know a lot of them, learned all of it in school and in university, normal and gamma and logit and whatnot. But there's also another part, which is on the right here, quantile defined distributions that are a bit more cryptic names, but they're pretty well developed in the literature. GNK, GNH, GLD, generalized lambda distribution, Govindarajulu, Wakibi, and many other distributions that are parametric, but they're defined by quantile function. And as you can see that they're not invertible, which means that they don't have a CDF, that is closed form. So that's the kind of setup. And then you have some distributions that have both of them, and those are very nice to work with. So in paper 2, I explored these quantile-defined, not invertible distributions that could be used for Bayesian statistics, Bayesian inference. And then in paper 1, which is another paper, I looked at quantile parameterized distributions. I'm going to talk about that in a second. So just wrapping up of these quantile-based inference, in Bayesian inference, this backward move of the models could be used using this density, quantile density, which gives the same result as a conventional likelihood using f of x. And it could be used as a prior. And then turns out that it actually simplifies the specification of the prior. And it could be very well used for expert elicited priors, especially when they are these quantile parameterized. I'm going to talk in a second. But also these quantile functions could be used as likelihood. They require root finding to find the corresponding depths. And then the paper goes in a bit deeper into what that root finding algorithm would need to be. But it turns out that these models are possible. And we also do some simulation studies to prove how efficient that would be. And as I started to talk about this parametric quantile regression, it's a particular type of regression which gives you non-crossing posterior quantiles by default. You don't need to do any smoothing, none of this thing that is required by regular quantile regression in Conker type regression. Here you get the result of non-crossing posterior quantiles, and that's very good for quantile regression. But as I said, it has some numerical part that needs to be included. So now let's talk about expert elicited distributions. So when we elicit judgments, we typically elicit this in some form of quantile probability pair. So here's, for example, fish weight. And here I'm trying to elicit from an experienced fisherman what the typical weight of a next caught fish from this reservoir, from this river, would be in terms of pounds of weight. And this fisherman gives me a median of 9 pounds and an upper quantile, 90th quantile actually, corresponding to 17 pounds, and the lower quantile corresponding to 4 pounds. This is a setup from some US-based, Canada actually based, fisherman data. And so anyways, so that's how judgment is usually elicited. And this setup is called symmetrical percentile triplet. And here we are specifying it symmetrical because it's symmetrical around the median. We have the lower and the upper quantiles that are symmetrical around the median, the 10th and the 90th. And here the tail is 10%. So alpha is 0.1. What we're interested in, we want to smoothly interpolate between these 3, sometimes 5 points, and fit some sort of familiar, maybe convenient distribution to them. Or we could use a distribution that is defined by these 3 points directly. Fitting would sacrifice some of the precisions of these 3 elicited points. But if we would have a distribution that is defined by these 3 parameters or pairs of parameters, right? Then we could have something that perfectly fits the elicited quantiles. And it turns out that these quantile parameterized distributions are exactly that. They are naturally suited to be used as priors because you can take the judgments, prior judgments, and convert it into the smooth interpolation between these 3 points so that you can sample from anywhere in that function. Or they can also be used as likelihood. It requires somewhat special specification of a prior, but that is explored in my paper 3, and also kind of touching back on paper 1, which introduces the whole type of distribution. Quantile parameterized distributions can be used to encode expert judgment. That's the topic of my paper 1 and paper 3 in the thesis. So just a little bit further into the woods with the quantile parameterized likelihood models. They are simple models that are based on judgments elicited from experts. The predictive judgments that I just described, let's say, of this next caught fish in the river, they contain no uncertainty. Yeah, I basically have these 3 points, but there is no uncertainty about those elicited points themselves. They are like, 3 specified precise points from the predictive distribution. But if you want to build a model around it, you need to admit uncertainty, either in the probabilities, the 10, 50, 90, or into quantiles, which is this 4, whatever was it, 9 and 17. So one of those need to be allowed to vary, or maybe both. And there are some examples in the literature. There are these two references that have admitted uncertainty into the quantiles, the numeric values of the weights. We took another approach, which is we admitted uncertainty, allowed probabilities in those triplets to vary. And therefore, our approach is that we have basically, you can see that in my graph here on the right with the fish weight. The probabilities are divided into bands. You see the gray and the purple and the kind of grayish and yellowish band. Those are bands of probabilities that are allowed to vary in the width. They will, as you introduce uncertainty, as you introduce ability to vary around those judgments, they will be allowed to either shrink or increase. And for that, you have basically a Dirichlet distribution. You have a discrete distribution that is going to describe how the uncertainty is embedded into that judgment. And you can do that with a special kind of elicitation that we also introduced in that paper that's called hybrid elicitation. And it's called hybrid because it has parts of predictive elicitation, but also part of parametric. It all stays into complete elicitation stays in the observable domain. So we never talk to experts about unobservable abstract parameters. It's always about observed fish, but it has a target. The purpose of that elicitation is to elicit parameters. It explicitly accounts for uncertainty and variability, and it can be used before parametric model is specified and available. There are some additional benefits that come from that type of elicitation that is explored in the paper as well. So distributions that are defined by quantile probability pairs, you see that my quantile function now has 3 dots. Those are defining points. They're defined, the distribution is defined directly by those triplets or more quantile probability pairs. And they can be useful for expert elicited quantities because whatever you've elicited, it becomes a parameter in the distribution. These distributions are created using one of 2 ways, either through reparametrization, and we have discussed some examples of that in paper 1. A Meyerson distribution is like that, and Johnson quantile parameterized distribution is done that way, or as a system of equations, and there are these examples that I'm going to talk about in a second. The typical reparameterized distributions, they're symmetrically, well, all of them that I explored, at least in my paper, they're symmetrically parameterized, which means that it's always symmetrical around the median and some sort of pair of points around the median in terms of probabilities. They can be explicitly or implicitly bounded, which means that sometimes it's yet additional parameters that you need to specify to set the bounds, or sometimes whatever you specify as quantiles will imply bounds. Sometimes they can lead to unintuitive tails. So here's, for example, both of these quantile functions, or rather the quantile function that I fit here, the blue quantile function, the beta doesn't fit any of the points, basically, as you can see there. I have judgment from the expert, and I'm trying to fit the beta distribution. This is best fitted beta distribution in red. It doesn't go through any of the points. It interpolates pretty well, but it actually doesn't hit any of the points. The blue distribution is super flexible Johnson quantile parameter distribution. It goes through every point faithfully, but then it produces this somewhat unintuitive tail, and it's because my Johnson quantile parameter distribution is a bit more flexible than beta. It's too flexible for 3 points. But with, let's say, 4 points or more, probably would be appropriate. But like that's something that you need to watch out when you're working with super flexible distributions that are able to precisely match. I mean, this is just a bad example, particularly discussed in the paper as a drawback of these type of distributions that they can be too flexible for the judgment that you elicited. The system of equations approach is based on the idea of linearly combining quantile functions together, and we have a bit of a discussion of feasibility conditions when this combination would be feasible quantile functions by itself. But the textbook by Gilchrist is laying out a lot of these kind of basic foundational blocks for building quantile functions that are feasible by design, by definition. They're infinitely extensible in the sense that you can have any number of quantile probability pairs. Sometimes they would require conditional optimization in order to fit that, but there are many efficient algorithms for handling that step. Also in the paper, we discuss how to extend quantile parameterized distributions into multivariate setting using standard methods. And not in the paper, but in kind of hinted towards in the discussion, and then in subsequent work, we're working on using quantile parameterized distributions to encode posterior samples, or rather approximate empirical CDF from some sort of algorithm. Say Bayesian algorithm has produced posterior samples, and you want to give it a closed form. So these distributions could be used to have closed form posterior, which is very useful for many things. All of these ideas are just building the foundational work for being able to incorporate expert judgment into real life models. So here is my case study that we've applied these concepts on. It's a case study for managing geese in southern Skåne. In geese management in particular, there is this tension between conservation objectives, right? We want to preserve these species and biodiversity and the basically feasibility of the species, right, the long term. And on the other side, we have an important objective, which is harvest, or rather hunting, which is used for recreational activity, for lots of things, and also to contain the population in optimal band. And many of these species, they also cause a lot of conflict with agriculture, especially in sensitive spring periods when the sprouts are just coming out, and larger birds like geese can trample and pick out very early growth, or rather affect the early growth of the crops. Management of these species require good estimate of distribution of species. So in a sense, where are they and when do we expect to find them there? There are plenty of data that comes from citizen science. Amateur observations recorded whenever you see something happening, right? There are these databases, including GBIF, very popular, and in Sweden, we have Artsportal, and that is very helpful, but these observations are done without any protocol, and therefore these observations are coming with preferential sampling bias. In preferential sampling bias, I'm going to talk a little bit more about, but basically it says that people that are recording observations that are either preferring particular locations, or they're preferring particular species, or both. And in that sense, it's not an randomly sampled data. We built a two-stage model that first predicts species richness across a region. This is northeast Skåne, with Kristianstad in the center and then some communes around it. Two-stage model predicts species richness across the whole region and then uses it as a benchmark for species list length. And species list length means that an observer comes out and they record a number of species on a trip, and that whole list that they've recorded, not only geese, but other types of species that they observed, the length of that list somehow should be representative of this richness, how many species are there in the area, if the observer is unbiased. If the observer is only watching out for eagles, then of course it will be eagles or nothing. And that kind of observation is not representative of the richness of the species in the area. And so therefore we need to include this attention thinner, we call it attention thinner, for probability of presence based on the shortage. The species list shortage is the difference between how long is the list and how rich the environment is in terms of how many other species we expect to find in that local area. Observers that are submitting longer lists are more likely following some sort of protocol. They're less prone to this taxonomic preferential sampling bias, which means that they're not referring to they're not picking out their favorite species. They're hopefully recording everything they observe. And then we have specified prior parameter for that using one of the quantile parameterized distributions that I discussed earlier. It's called generalized Meyerson distribution. So this paper 4 is introducing expert-informed attention thinning that is supposed to reduce prediction variance and ameliorate the preferential sampling bias that I just discussed in a second. So as a result, I want to kind of wrap up. We have built this species distribution model for geese in Skåne, species list length approach that we've taken tracks all bird species and builds the first stage model to estimate the richness, and then uses that species richness as a benchmark to estimate how far from the ideal state is the particular list that is contributed by the observer. Priors for the thinning parameter is specified by quantile parameterized distribution. As a result, observations with longer lists are less taxonomically biased, so they're constituting a relatively small portion of GBIF. So very few people contribute long lists, but they are actually the only data that is sensible for modeling. Majority, 99, I'd say, % of the data is useless because it's biased. And this expert-informed thinning that we've introduced allows for it basically contributes to reduced prediction variance and improvement, relatively minor improvement, but still improvement in precision as well. See here you have box plots that are showing basically the baseline is on the bottom, and then in almost all models you see shrinkage of variance, and in some case it's also like minor improvement in mean, for example on David Sebastiani metric, also on log metric, but not in absolute error, and maybe not on the standard error. My thesis contributes to advancement of this quantile method for statistical inference. We've explored quantile parameterized distributions that can be used to capture expert knowledge, both for priors and for predictions. The case study that we've applied these knowledge to shows that we don't just need more data, we need better collected data. Data collection determines the usefulness of the data, and it's not enough to just have more of it. We need to have a better, more disciplined way of collecting the data. These are the papers that are included in the thesis. I encourage you to go to this URL and look at the whole thesis. Papers and COPPA are there, and this is the cover image that you don't see in the PDF, but it's AI generated. These days, everything is AI generated. So thank you for your attention.
Excellent. Thank you so much, Dmytro. Just like recently, we're opening up to questions if anyone has them. But let me start off with the same question I asked earlier. What is sort of the most profound revelation for you doing this research?
Profound revelation is actually, I started my PhD with this burning question in my skull. How can I use expert judgment in the models? I've been working in oil and gas in the past, and it's all based on expert judgment. And it's been always, expert judgment was there, and then there comes statistics, and they have their own models, and then these people could not talk to each other. So I had this burning question that I spoke to my supervisor and said, like, this is what I want to investigate. I want to understand, how can I bring these worlds together? So this was most insightful for me. Well, there is a way of doing it, and it opened up a whole new world. I'm passionate about this, and I keep digging and discovering more and more. This is very inspiring. But in terms of case study as well, the discovery is that 99% of the data is junk, and you're actually wasting your time if you're digging or trying to find something there. In a sense, big data is a bit an overpromise because we have not paid attention for how we collect the data in many systems. We have not been very careful with collecting data. We've accumulated by now gazillion terabytes of data, but a lot of it can be as useless as the data that I've studied. But it's possible still to do best and try to squeeze out signal out of the noise. And I've discovered this case study is using INLA. Super cool. I want to give kind of highlight that if you are interested in INLA, check out this model. It's very cool, and lots of things you can do to attack the bias and try to get most out of the data, and maybe even subset the data to make most of it. So that was also a great learning experience for me.
All right, excellent. And if you were to redo this study with the knowledge you now have, what would you do differently?
I think so. It's a very good question. I think that so right now it's one big model that tries to handle all these species together. I don't know if it's very, or let's say if it's a small step, it sounds like it's a relatively small step, but it could turn out to be big step. But I would love to fit simultaneous models per species. So in a sense, I have one model for all species. I'd love to have maybe 12 or 15 models that are attacking each species individually, and then have some sort of pooling multi-level model where I would pool the individual inferences from each of the parameters on the model into a common model. I think it would help attack some of the differences in abundance and particularly in sampling patterns across models. It sounds a small step, but in terms of math and complexity that it adds, especially with spatial covariance, it can turn out to be prohibitively expensive. I don't know yet how I would do that practically, but that's the step that I feel compelled. And there's evidence in the literature that that's the avenue that other, let's say, similar models are going, is simultaneous modeling of multiple observation processes.
All right, awesome. Yeah, that does sound complex and would probably require quite a lot of computational power to accomplish. All right, do we have any other questions from the audience? It is also perfectly all right to ask your question in Swedish, and we'll help out translate it.
Absolutely, yeah. That can be.
Claudia from Grimson, again, please.
Yeah, I have an interest in this. I work a lot with agency people, and we have typically these problems like there needs to be a formal decision to be made. Is this lake of good ecological health or not? And there's very little data, and there's a lot of expert knowledge, and it might not fit into your expertise here because the data is so sparse. But my question is, working with agency people, do you think you can convince them? I mean, you talked about that they do not communicate well with the decisions, and the decisions not with agency people. What is your experience how this communication can be simplified, and will your models make it easier, or will everybody only be like overwhelmed?
Thank you for the question. It's excellent. I think that transparency goes a long way, and if you just show the goodwill and really openness for dialogue, then there is higher chance that dialogue will happen. I think that it's essential to set up the decision model, even if you don't have this statistical model behind. You can set up a decision model and have experts specify the outcomes. That's also absolutely possible. But this part is, if it's transparent and understood by all parties, it can function by itself. Like you can have statistics almost on outside. It can be informed by expert judgment by itself, but the transparency in the setup will allow good, useful dialogue. The decision model can be specified separately. It can be informed by the data if you can, but if you cannot, experts could be still useful for specifying that. But kind of being clear about values, being clear about things we can do, being absolutely kind of rigorously and transparent about the frame, how we conceive of the problem is essential. Lots of things have been done in this domain. Please check out prescriptive decision analysis. I can give you references. It's a domain that I've been passionate for a long time. It works in many industries, including environmental domain as well. Somebody by name Michael Runge is a name that you can kind of pull the thread on. Check out, kind of search his name, and then he published books, and he's been part of case studies that have applied decision analysis, structured decision making, it's called, in environmental domain. They have a couple of textbooks and case studies. Michael Runge.
Perfect. Once again, thank you, Dmytro.
Thank you.
I see that Viveka is already here. Very warm welcome to you.
Thank you very much.
Viveka, you have been working in the field of environmental statistics for, what is it, almost 30 years?
Yeah, sort of.
I think it's fair to say that you are an expert in this field, at least. So right now we are very eager to hear your thoughts and reflections on these two pieces and sort of from your point of view, what they bring to the table.
Thank you very much. So hello everyone, my name is Viveka Palm and I'm working at Stat Sweden. During the years when I worked there, I've mainly been involved in either the environmental accounts, which bring together environmental issues of various kinds with the national accounts. So basically making a portrait of how the various industries in Sweden are using materials, what type of emissions they have, and what taxes and subsidies they are facing. I've also been involved in the Agenda 2030 follow-up with the Sustainable Development Goals, where we have spent quite some time discussing with people what type of statistics, indicators, numbers we could bring to follow up those the targets that were made and how we could describe society with those. So I'm very pleased to be here. I'm very happy to hear these two excellent examples of what can happen when you're trying to get numbers to make sense for various types of questions. I think I will start to ask the questions sort of in the opposite order. I will start with Dmytro, if that's okay with you, Dmytro, because we have been looking at the red list to try and understand how we could possibly make some information about biodiversity within the statistical system. Since the statistical system is sort of made up by the statistics that the governments have decided that they need to follow up the society in general, there has been a large, I mean, the main products that all the statistical systems in the world concern either population, social statistics, or economic statistics. So I should also say there have always been agriculture statistics. There have always been an interest to see how humanity sort of interacts with the world that is around us. But when we have been looking at biodiversity and this red list, there has been a discussion since some time about citizen science, where sometimes the statistical officers are being asked to bring on more of this type of sort of self-collected information, and sometimes we actually do. So I would want to say to you, Dmytro, that I think that when we have looked at it, we make a separation between there are some of this information that's being gathered by societies that are very interested in some specific birds or some specific butterflies, and they then set up quite rigorous systems where they check the same things every year, and they have a clear model of why they're looking at what they're looking at, and they know what it is that they would like to follow over the year. So I would say that those types of time series contain quite a lot of information. And then on the other hand, you have this more spurious information where perhaps you ask people to report whenever they see a dead seal or something like that. And then it is not so clear how this information sort of really has a system where you could really say what type of a question are we getting the answer to here? Will it only be the seals that are in the most popular areas that we will ever see? What does it mean for the entire population of seals being dead or whatever? But when I sort of speed read your thesis, what I wasn't quite sure of was you say that you don't think the data was really good enough, but what was it you would have wanted to have? Like, what was your, if you had perfect data, what would that have been? Because your question is more like, what do we want to do with these geese, and do
Yeah.
we want to hunt them or do we want to keep them? But what would be your ideal?
Yeah, I think so. Thank you. Very good question, and you're absolutely right. That I mean, I'm sitting in Lund University, which is author, or let's say maintainer and responsible body for Svensk Fågeltaxering, which is a disciplined way of assessing. But the problem is that it's too sparse, and it's in the grid, and it has it has some limitations. Anyways, the citizen science is of course much more abundant. But what I want to do, I think, like one of the examples of successful application, I think, is primarily US. In Canada is covered by eBird system, where the citizen scientists are encouraged to collect data using species list. You can't just record things that you have just observed. You need to, you open the list and you check in through the list. It kind of nudges you towards a bit more disciplined and civilized approach. And I think that's an excellent example of rather introducing best practices of data collection, even for people that are not trained in data collection, if you know what I mean. Like, we can create systems that are nudging people towards good data collection practices using, modern technology, for example. Another one, which is I've trained in, of course, in terms of geese, Denmark is very good in doing geese statistics in particular, and they have wing surveys, and they have mandatory reporting of every hunt from every hunter ever, and that helps a lot with quality of the data, which is not mandated in Sweden. And you could say that it would be a relatively small implementation because we have, as you said, societies and hunter associations and everything, and they probably would be willing to kind of submit that data. It's just that they're not asked to. And so going after these low-hanging fruit of enforcing, or rather nudging people towards good data collection practices, and asking people that already are prepared to give good data to actually start contributing that data, that would contribute quite a lot to improving quality.
Thank you. Yeah, for 2 very confusing weeks in my life, I spent them in a bird sanctuary in the middle of Sweden, and together with a lot of people who knew something about birds, which I did not. I was sort of carrying around stuff and making small bird houses and doing things that you can do without knowing the difference between a small bird and a big bird. But I was very surprised by the expertise that went into these, because basically they would be looking up into the sky and say, okay, there passes 100 small yellow birds, and I would not have been able to neither see what birds there were nor how many there were. So in the sense, this is there is it's nice if people have this expertise that they can really bring to the table. But I agree with you that, I mean, some hunting statistics would probably be a very good way of doing it, because there are people who are sort of self-interested. They probably know what they shot, and so that would be a good way of getting more information on the geese. The wing statistics, I don't really understand. What's that?
So in Denmark, they have lottery among hunters for cutting out wings and sending it to a statistics bureau that measures them, and that and then lottery is gambled among the participants of that survey. What it allows to do is allows statisticians to go deeper into population and estimate the structure of youngsters versus older birds, repopulation dynamics. It's like it's a whole new level of detail into the data, just by making a small incentive for hunters to send in. It's a mail-in survey. You cut out the wings and you send it to a particular address that everyone knows, and then one person out of the whole country wins something like a small gift or something, but everyone is participating.
Thank you. Another way that we have tried to understand what we could do with biodiversity is that there is a legislation where you report how many species you have that are in danger, but you also report on the habitats that they have. And what we found was that it's a lot easier to observe and to say something about the habitats, because they are there all the time, basically. And so when we tried to do something that we could be comparing between the Nordic countries, we said, let's not look at the species, but let's look at the spots that are disappearing, which I think when I looked at your model there about, what do we want, what are the alternatives, and then basically if you want to keep the species, what we can do is that we can try and preserve the habitats. That's much easier to do than sort of changing the weather or asking people to stop shooting birds in the Mediterranean area, etc.
Correct.
So yeah,
I want to just mention that Norway is very successful in that. They especially in Trøndelag area and a bit further north, they do both sampling, data collection, and modeling of habitats for migratory birds. So there's a lot of knowledge there that could be borrowed.
Thank you. And that we do have a lot of Nordic cooperation. I think it's a very good way of sort of extending. A few people here and there can sort of together make a much larger impact on this system in general. So thank you very much. And with that, I will turn to Michelle. And I was very happy to see your study, and I also realized that part of my PhD study was to try and measure how some trees take up cadmium. So I was also elaborating with these soil columns and using a hydrological model to try and understand how much of this cadmium could sort of come together with the water out of the soil. And the complexity of sort of going from 1 square meter to something that you want to extend to many different types of soils is quite mind-boggling. So I was very impressed by the study that you did, and one of the questions that I would want to ask you is, you are now working at the Swedish Hydrological Institute, so I wonder, can you apply any of this with the questions that you are dealing with now?
You need to unmute yourself, Michelle.
Sorry, I work at the Swedish Geological Survey, so I don't know if they were a bit mixed up with SMHI, but
Yes.
the SGU, but they work with groundwater. And yeah, but they actually apply a lot of statistics and things like that to characterize groundwater systems and aquifers of varying size to get a sort of homogeneous picture across the whole country, similarities between different regimes in terms of climate, but also the geology in terms of bedrock, in terms of soil type and diagenesis, so how the sediments were deposited and things like that, which in turn affect the groundwater storage. So they use the time series that they have in addition to other data to characterize them and to get the responsiveness, sensitivity to climate change, sensitivity to water scarcity in particular, something that they work, especially in the summer, with sending out like warnings in collaboration with SMHI and other places. So it's similar methods, but I recently started, so I'm getting into it.
Okay, yeah, that's fantastic. I was also wondering, because you said that Sweden and maybe also Finland have quite shallow aquifers, so in some sense there cannot be a lot of water being stored there. So maybe you were happy then that it rains quite a lot. I don't know, but I was wondering if you would have done a similar study, say in Denmark or in Italy, do you think you would have found completely different patterns, or do you know anything about like what does it look like if we would sort of look a little bit further to the south?
Yeah, I mean, we can also look at Sweden actually. Like I said, generally in Sweden and Finland, it's like this. But we have I think it's called Kristianstadsslätten. There's a big, I think it's a sandstone aquifer with quite a lot of storage. And we have other places in Sweden with sandstone and limestone where you have a much higher storativity, and then it can, like the memory of the aquifer can be years and years, and then you need to look at, like, then it's more important, these periodicities that you see over longer periods, like wetter years and wetter and drier years, and then you can, the sensitivity to maybe short-term anomalies can increase, because in general it's been a few very dry years. So yeah, like this, for example, I looked at response time and memory, and another thing I wanted to do, but I didn't have time to, was to look at how these things change over time, because I was looking at a 15-year period, but even within this 15-year period, if you shorten the years, I mean, you have different patterns coming back all the time, and this response times, the memory, it's not static. And that's something that's discussed often in hydrology and in climate studies. Like, do we assume, I forgot the word for it now, but do we assume the system is static or that it will change? Because in reality, we know it will change. So, well, to answer your question, yes, it's very different for the south with the higher storativity, but also, as I saw a connection to climate in general, like these things change over time. So I think you could get probably a time series of how memory changes between years. And I think that's something to really take into consideration. You look at future climate impact and also how to mitigate this impact. And I know that Denmark is putting a lot of money into this because they're so dependent on groundwater for their water supply. But I actually don't really know any specific results like this on the top of my head. But yeah, like huge variability spatially.
So could I ask you, what do you think, like how much does it matter what is growing on the soil? Like if it's a forest versus if it's a field? Is that something that you have been looking at, or how do you think about vegetation in this?
Well, it depends actually on the capillary fringe, as I mentioned. So in part, it depends on how deep below the ground surface the groundwater is, and then also a little bit on the root depth. But typically, for it to have an impact, or to have a larger impact that you see on the time series within a year, the groundwater level should be maybe 1 or max 2 meters below the ground surface. Then it's very sensitive to the kind of vegetation and the kind of land use. But in some places, in chalk aquifers in the UK, for example, the groundwater level can be very, very deep, several meters below the surface. But because of the porosity, like the small pores of the rock, in some periods, there's a hydraulic connection between the roots at the surface and the groundwater very deep down. And this can lead to, especially in dry periods when there isn't so much precipitation, so the soil is dry, you get this very thick capillary fringe, and then the groundwater can be depleted even more by direct transpiration. So how drought resistant the plants are and how much water they require to continue growing can influence the amount of groundwater depletion in the summer and the rate, and yeah, like basically how deep it will go. But this is also sensitive to the geology. So, well, the geology can sort of determine how shallow the groundwater is, but also if there is possible to create a connection. And I think, if I remember correctly, you need to have quite small pores for this. So I don't think in an S-grid that it would happen. But I can't tell you immediately, well, what kind of crop is better or kind of forest is better for one thing or the other, because it depends on what you want from the land use. But yeah, it can have a huge impact.
I've been spending some time in Luxembourg, and one of the things that I learned after a while is that they have Roman aquifers there. They have built there's a very weird thing that's where the groundwater is sort of connected from deep underneath the soil, but it's still being transported. I wish I remember the name of it, but I do not. But I don't know if you maybe know something about such, because they are man-made and they keep
Oh, wow.
water also in extremely dry weather. But yeah, I forgot the name of them.
Super cool.
Yeah, they are definitely super cool. They had sort of dug one out so that you could actually go into the mountain and sort of see it from the side. But
So it's like an artificial cave.
it's like an artificial underground water system, and they made a cave so that you could sort of look into it.
Okay, wow, that's super cool.
Thank you very much. I think we are ready perhaps to open up for questions from the audience.
Exactly. And if I could ask Dmytro, exactly. So we are now opening up for questions from the audience to ask all three of our wonderful presenters. Thank you very much, Viveka, as well, for spearheading this Q&A. We do have a few questions prepared for our panel discussion as well. So I will start that off, and if you in the audience feel that you have a question you want to pose, just raise your hand or fire away. But we've now heard these two excellent pieces and also heard from you, Viveka. What has to the three of you been sort of the most interesting to hear about during this afternoon? We'll go in the order that you presented. So if we start off with Michelle. Don't forget to unmute.
Always. I think, I guess it's understood, generally assumed, but just to hear about how frustrating it can be about data quality and data collection practices across different fields. I feel like in many cases, I'm sure that we collect very good data on some things, but I'm sure that in many cases in terms of environment that we could learn a lot from other countries. But I think it's also a question of incentives and things that we need to get policymakers to implement to prove that the data we need is interesting. I have no idea how to do that, but yeah, it was very interesting to hear Dmitri's perspective on this.
And Dmytro?
I am fascinated with geology, and I've been kind of fascinated with people that make sense of what's going on underneath the ground. I sometimes, if I can offer a joke by geologists, they said that geologists and priests have something in common. They talk about things they've never seen, and that kind of rings the bell. But it takes a lot of things, lots of statistics, knowledge, lots of assumptions, and diligence, and excellent work. So thank you for bringing geology into picture today. I'm delighted to follow along with that.
Excellent, thank you. And Viveka, what's been your takeaway so far?
Thank you very much. Well, I have to say I really appreciate how much knowledge that goes into every aspect of what we are measuring, and there is sort of no end to the news that you can find. You know, whoever you talk to who has been sort of diving into something, there will always be something new to learn. So makes it like I'm hopeful that we will get even better and more environmental statistics with a lot of help from, not least from all the various institutions that are sort of providing data on their expertise, and of course from the many PhD students that are sort of slowly but surely expanding the knowledge that we have. So it's a lot of fun. I didn't know that we were sort of that there was actually some Bayesian mathematics behind the red list, but I've now sort of checked and realized that they actually do. So that's also amazing to see.
Awesome.
And of course, I didn't know so much about Svenska Statistikfrämjandet before either, so that's also been really nice to look into.
Excellent. We did our part as well.
Can I have a small kind of action suggestion here? I mean, we are a perfect buddy here, Statistikfrämjandet and people that are interested to actually take action maybe towards society and initiate maybe some of these changes in data collection practices, you know, bring it up for public awareness that, hey, we could make a difference, we can make an improvement. And who else? I mean, I've spoken to some of the academics and they're like a little bit kind of shrugging their shoulders and saying we don't have ability to do anything, but the society probably could spearhead some change, and I think that we're in position to do the difference in this area.
That is an excellent suggestion. I do believe we have our chairman of the board, Nancy, with us as well. Nancy, will you make a note of that, and we'll take it up on Thursday on our next board meeting. So, Dmytro and Michelle, you presented this in 2022, your respective pieces. Have you seen any practical use of your research? Has it been used in a practical setting so far?
Michelle,
would you like to go first?
Oh, absolutely, I am. So yes, in other industries, there are applications of expert judgment, and some of the distributions that I've studied actually come from and will be used or are used today in those industries. So that's promising. But also the types of models, for example, this inhomogeneous Poisson process that I've used has been applied in other areas. I know of one model in Scotland that is based on the model that we've developed. There's a researcher in Italy that reached out and said that he's doing his thesis and he's relying on some of the things that I've contributed. Anyway, so there's some things that are going on. It's a very short time gap. I've just defended this January actually, so it's still fresh off the press, but hopefully, yeah, it will have some impact.
Excellent. And Michelle, have you seen any use for your research?
Well, I don't know how relevant. Like some journalists are a bit interested. I think just because it's a hot topic with the climate change, and as I mentioned, the more I look into it, the more uncertain I am about my results, and I would like to study them more. But I know that at SGU we do a lot of similar work, and I'm just super looking forward to applying some methods that I have used before, but also applying new methods and learning new things and applying them to our data and to try to improve the kind of data representation that we have and sharing to the public, and also in terms of information on storage and climate influence and what do you call it? Now I forget the word, but resistance is not the word, but the ability to withstand effects from droughts and things like that. So I will use my research to move forward.
Thank you. We have a question from Claudia from Brömsen.
Yeah, I would like to ask you a question, which is, so environmental problems in general are really quite complex. We have a lot of different pressures. We have climate change, we have land use change, we have biodiversity that is very difficult, very complex to observe. There is a lot of data, but obviously never enough, because the questions are so difficult. But I also feel that there are very few statisticians that work in this area, and especially work actively. Then, I mean, you are at SGU at least, so you work from the inside. But many of us statisticians are like on the outside. We make a model, we think that this would be good, but we have quite few. and there are also not too many people here today. So how should we work for more statisticians to be part of the environmental problems? How can we well, motivate students to work in this direction? I know that the agency, Statistics Sweden, has the environmental statistics part, but the Environmental Protection Agency doesn't have any statisticians employed. What should we do to make it more of an everyday topic for statisticians and for the agencies?
Dmytro?
Yes, it's a burning question in my head as well, and thank you for asking this question. It's excellent. I have two philosophical musings on this. First of all, we have at some point in time stated that we want to do value neutral science, and that has distanced us from decision making immediately. We didn't realize we shoot ourselves into the foot, but now we are not at the table when decisions are made, unfortunately. So first of all, we need to be a little bit less hesitant to participate in decision making where values are brought to the table. So objectives, what is it that we want? Well, how do we define biodiversity? Things like that. And also learn decision making skills, which is, for example, decision structuring, helping decision makers wrap their head around the problem is a skill that statisticians are very well equipped to handle. It's just like we've never prioritized that area. And that's a skill I don't see a reason why not statisticians can be helpful at. It's just like we've not taken that as part of our profession, but it could very well be that we can help decision makers structure the problem and inform them in disciplined scientific way. And by scientific, I mean rigorous, disciplined, systematic, rather than value neutral.
Excellent, thank you. And Michelle?
Yes, from the employees and student perspective, I think that, I mean, it's moving in that direction, but I think we really, really need to work on interdisciplinarity. Like, I remember as a PhD student, many of us were applying statistical methods and like trying to attend courses, trying to learn a bit online. I applied to Bayesian models in my master thesis, and I spent so much time on YouTube. And I felt like I need time for 2 degrees, one in statistics and one in geology. Like, and I can't quite do both. And then it's like also I have to, like many researchers these days have to also be developers to a large degree, or modelers, or there's so many expertise that goes in, and really like everybody can do it all. It should be like a team. So I don't know, like I know that Lund University is applying more interdisciplinary like research projects where you're getting people from humanities, from law, from economics, from the environment side to tackle similar problems to do with Agenda 2030 goals, for example. I feel like we need to incorporate this more into research, more into the state agencies, like from when the students are bachelor students or maybe even high school, I don't know, like to get people maybe interested in their nerdy topics, but to force them to interact with each other and to always think a bit holistically, even as they're looking at the thing that they're very good at their small problem. And I think it's moving a bit in that direction, but I think we need more incentives for this. And I think that comes from the research grant side as well as how we phrase our research questions. So yeah, I'm also interdisciplinary is very interesting. I think we need more of that everywhere.
Thank you. Viveka, would you like to lean in on this as well?
Yes. I was, like Dmytro is saying, that we're taking a stance where we're not policymakers, and I think that's very true for the statistical offices as well, that we're providing information, but we are very careful not to make subjective assumptions into what we're doing. And if people are asking us for answers to questions that really need to have a lot of assumptions in them, then we typically ask researchers to help out so that it's it's not sort of seen as something that comes out of a stats office, but it's something that's built on statistics. I also agree with Michelle that I think from the university side that it is becoming much more vital to know a lot more about programming, and that sort of leads into mathematics, and that sort of also leads into statistics. So I think it's a little bit more popular now than it was some years ago. And like you said, with YouTube, it's also a little bit more accessible. So if you don't understand what your teacher said, you have some other options to go and find someone who's perhaps a little bit more able to engage with people out there. So I'm still hopeful that we will gradually build a really good information system. I would also want to say that I really felt that the SDGs and the way that they were set up in the whole world really got a lot of us statisticians together in new constellations that we had not been before, and that felt quite. It felt like that was a movement that made more people start to do what other people were doing. But yeah, we will have to use this fabulous internet and continue to learn from each other. Thanks.
Excellent. So looking at the other side of that coin, how can we also increase the impact that scientific research have on our society? Not just having more statisticians in environmental science, but also making it count in the other end. Michelle, would you like to start off?
Yeah, I was at an interesting conference a year ago called the HAPEX. I think I actually can't quite remember what it's called, but it's about the hydrological forecasts extremes, and there's a lot of researchers from different fields looking at hydrological forecasting. It's a lot of AI and these kinds of things, and you got a huge output with different distributions and probabilities and all these things. And one point of the conference was to sort of take a step back and be like, wait, who is asking for, like, who is the audience? What kind of information are they asking for? What can they handle? And as someone who previously worked with hydropower, I've seen that, like, I think with some time I can analyze and disassemble complex information, but if you need to make a decision within an hour and you don't have more time, you can't sit with like all of these different quantiles. You need, like, I need one number for this hour, I need one number for the next hour. I cannot handle more than that. And that's a problem in like how we simplify it to make it manageable, depending on the target decisions to be made, also dependent on the background of the audience. So who is actually reading this? Do they have an understanding of the topic, or are they completely green? I think for the impact to really be felt, we need to really think about this side as well. And that is, I think, a different aspect, like a different field, but maybe something to think about more for yeah for people we want to see our research and to use it for them to be able to actually.
Excellent, thank you. And Dmytro?
I'd love to advocate for thinking about who are the future decision makers. So the people that are in college today, they're among our students if you're teaching, and they are in non-statistical disciplines, right? They're somewhere in management sciences, they're maybe somewhere in engineering, I don't know. So they will become future decision makers. So what we teach them today about decision making, statistics, will eventually trickle down into decision making on society level. So we need to be thinking today, what is it that we want to indoctrinate them with, if you want to say, but like a very, very precisely what is it that we want them to know in order to, yes, call us when they need us, or at least recognize that they need us, but also maybe avoid some common pitfalls that are happening, or we know of them anyways. So that is how we make a difference. When we teach others, we need to be aware that we're teaching future policymakers and be kind of tailoring our approach in particular ways to address that.
All right, excellent. Good point. So final question. We've spent almost 2 hours together listening to your excellent thesis about various environmental research and statistics, and also Viveka's excellent penetration of how this then applies in a practical setting. So what will you do differently as of Monday as a result of this webinar? Dmytro.
Yeah, it's hard to say what I would do differently, but I definitely want to be more active in communities like this and be able to speak to like-minded people and maybe like jointly try to make a difference. So it's good. This is excellent that we can reach out to each other and exchange ideas and also maybe build a case for societal change. So thank you for organizing this. I want to say high five to you reaching out to these PhD students and inviting us to present and informing us about the society. Thank you.
Excellent. Thank you so much, Dmytro. And Michelle?
Yes, I think it's a great community to have, and I think together we can make some change. I would also continue to advocate for better data collection practices, since I hopefully will be more involved with that soon.
All right, excellent. Thank you very much to the both of you, and also thank you very much to Viveka for participating in this webinar about environmental statistics.